In this lecture, we're going to continue talking about subspaces. And what we're going to do is work through a somewhat lengthy example where we look at different sets in R2 and determine which of them are subspaces and which of them are not. And after doing that example, we'll have a better idea of what it means to be a vector subspace of R2, and we'll write down some properties and summarize what we've learned. So the example that we're going to be looking at is of 4 different sets. Sets A, B, C, and D. And we're going to plot them, we're going to think about them and try and show which of these are subspaces and which of these are not. There's 2 of each. So the first thing we should do is let's note what kind of sets these are. All right, so A is the set of points x, y that satisfy 2x plus y equals 0. Oh, good. So this is a fairly standard set. This is going to be a line. So A is a line. It's the line y is equal to minus 2x. B is also the equation of a line. So B is a line. It's the line 2x plus y equals 3, and so we could rewrite this as y equals minus 2x plus 3. So it's kind of the same version of the line of A, but shifted up by 3. Now, our set C here is the set of points x, y such that x squared plus y squared is equal to 1. So C is a circle of radius 1, centered at the origin. And then D, we have yet another line. D is the line y equals 3x. So let me put down a plot of these sets that we're going to be looking at. So we have 2 lines that go through the origin, 1 line that does not go through the origin, and a circle. Now, because I've told you that 2 of these are going to be subspaces and 2 of them are not, you can probably deduce that the circle and the line that doesn't go through the origin are the ones that are not subspaces, which is true. But we're going to go through this very carefully and parameterize these lines and see what really breaks down in terms of the axioms that make up something being a subspace of a vector space. So let's make ourselves a little bit of space. And then let's start working with A first. Okay, we see what these are. We'll move the picture over. Now for A, what we want to be showing is that if V1 and V2 are 2 points on the line, then V1 plus V2 is also a point on the line. Because remember, a point on the line is a coordinate x, y. And the coordinate x, y also determines the vector xy. So we can parameterize the points that are on that line. I can take my 2 points, or vectors, v1 and v2, in A and write them as, in the case of v1, t1 minus 2t1, and for v2, t2 minus 2t2. And where does this parameterization come from? Well, it just comes from the equation of the line. So for A, my equation of the line was that y was equal to minus 2x. This equation relates the variables x and y. Y is dependent on x, but x is a free variable. So x can take on any value it wants, 0, 1, 100, 37, and that determines what y is. So if I take x to be t1, then y is going to be minus 2t1, and that's what I see here. Now observe what happens when I add v1 and v2 together. When I add v1 and v2 together, I add them component-wise, so I get t1 plus t2, and then I get minus 2t1 minus 2t2, which of course I can rewrite slightly as t1 plus t2, comma, minus 2 times t1 plus t2. Now this is essentially something of the same form as v1 or v2. I could rename t1 plus t2 t3 if I like, and then I would see that this is t3 and minus 2 t3. So v1 plus v2 is again a point that is on the line. t3 will also satisfy the equation. t3 minus 2t3. I can do the same check for scalar multiplication. If I take a scalar c times vector v1, then I multiply through component-wise and I get ct1 minus 2 ct1. Which is the same thing as, using more parentheses, ct1 and then minus 2 times again ct1. So I see that I obtained something that is still in the set A. And so A is closed under vector addition and A is closed under scalar multiplication. The check that we do for the set D is going to be very similar. For D, it becomes an issue of just parameterizing it and then performing the same kind of check. So we'll jot that down. This was how it worked for A, and similarly for D, we can parameterize things as T1, 3T1, or T2, 3T2 for our vectors V1 and V2. And vector addition and scalar multiplication are also going to produce things that lie on the same line. But this is starkly different than what we see for the line B, and certainly for the circle of radius 1. This does not work for B. For B, we need only find one counterexample. So let's just jot down a couple of points on the line. So B is y equals minus 2x plus 3. All right, let's copy that down here. Y is equal to minus 2x plus 3. So we could take, for example, the point 0, 3. That lies on the line. And let's add it to another point that lies on the line. Let's take x to be equal to 1, and then we will get y equal to 1. So 1, 1 is another point that lies on this line. But when you add these two together, you get 1, 4. But 1, 4 does not lie on the line because minus 2 times 1 plus 3 is certainly not equal to 4. So this point does not lie on the line B. You cannot do vector addition and remain on the line. In this example, what we're seeing is that lines that go through the origin have this property. But even straight lines that do not go through the origin do not have this property. I'm not going to explicitly work things out for the circle of radius 1, but I encourage you to take pairs of points on the circle and try seeing what happens when you add them together. Do your new points lie on the circle? Probably not. So let's summarize some of what we're seeing here. So in the cases of A and D, these were the two sets that really were vector subspaces. These functions that describe the lines were actually linear functions. And what that means is that f of x1 plus x2 is equal to f of x1 plus f of x2. In the case of A, that's this expression. And the other thing that needs to be true for a linear functional, f of cx is equal to c f of x. These rules are going to be violated when your line does not go through the origin, like what happened with B. And C, the circle, was also not a vector subspace of R2. There's another important observation here, and that's that when you do have a vector subspace, the zero vector must be contained in that vector subspace. So in the context of a line in R2, if that line does not go through the origin, then it does not contain the point 0, 0. So a quick check for B, and also for the circle C, is that the point 0, 0 did not lie on that set, and so neither of these could be a vector subspace. At this point, we're prepared to completely classify what the vector subspaces of R2 are. There are three possibilities. Your vector subspace can just be the zero vector. We would be talking about a single point, the point 0, 0 at the origin. That's a bona fide vector subspace. It's just a zero-dimensional one. Or you could have a line through the origin. And then the last vector subspace of R2 is all of R2. And this is the only thing that you can have for a vector subspace of R2. Before moving on to R3, let's look at another quick examples. So let's take something very similar to what we had before, but let's take a circle and let's take a quadratic. In this case, we're taking the circle of radius 1 that's centered at 0, 1. Now this circle does run through the origin, and our standard quadratic y equals x squared also does run through the origin. So for these examples, we can't take the quick check and rule them out by saying that 0, 0 is not on the set, because it is. The issue with these spaces is that they are not going to be closed under vector addition. And you can convince yourself of that by taking pairs of points that lie on these sets and adding them together and getting some other coordinate that doesn't lie on that set. In the case of the quadratic, you could take, say, 1, 1 and 2, 4 and add them together, but 3, 5 is not lying on this quadratic because 3 squared is not equal to 5. And for the circle, you could also take the point 1, 1 and then 0, 2. Adding these together gives you 1, 3, but this doesn't satisfy the equation either. And so for these examples, you really do need to look at vector addition in order to argue that they are not vector subspaces of R2. So let's do one other quick example, now looking at subspaces of R3. I'm going to take two sets. In the first case, A, we're going to be looking at the set of points, and now there are 3 coordinates to these points. So x1, x2, 1. So specifically, we're fixing the third coordinate to be 1. I would visualize this in the following way. I have a plane that's sitting here and going through 1. And in the second case, we're going to be taking a set of points x1, x3 in the third coordinate, and then what x2 is going to look like is if we add x1 and x3 together. So this is a kind of visualization of what this space looks like. Now, both of these sets describe planes in R3. We're talking about straight, flat spaces. They're two-dimensional and they're planes in R3. But one of these planes goes through the origin and the other plane does not go through the origin. If you think about the first case, it doesn't look like it's going through the origin, but also 0, 0, 0 cannot be described as one of the points in this space because 1 is the third entry of everything here. But 0, 0, 0 is in the second set because clearly taking the first and third entries to be 0 forces the second entry to be 0. So the purple plane does go through the origin. So that observation alone is enough to rule out the first example as being a vector subspace in R3. It can't be because it doesn't contain the 0 vector. In the second example, B, we're going to start with the observation that 0 is in W to make the point that W is non-empty. And then we're going to use the vector subspace check. We're going to see that it's closed under addition and scalar multiplication. So let's now take a pair of vectors that live in W. So we'll have the vector V, which we're going to write now as V1, V1 plus V3, V3. And we're going to take the vector U, which we can write as U1, U1 plus U3, and U3. These are generic vectors that live in W. There are 2 points on the purple plane. When we add V and U, we add them component-wise. So we get V plus U. We get V1 plus U1 in the first entry, V3 plus U3 in the third entry, and then in the middle entry we add these together, and we get what is the sum of the other 2 entries. It may be easier to see this if you rename V1 plus U1 as X1 and V3 plus U3 as X3 to really see that this is X1 plus X3 in the middle entry. But we get something that's of the same form. Likewise, when we do scalar multiplication, we also get something that's of the form entry in the first spot, entry in the third spot, and the sum of those 2 entries in the middle spot. So the set W is closed under vector addition and scalar multiplication. We checked the 3 things that needed to be checked to conclude that it is a vector subspace of R3. So in the case of R2, there were 3 things that could happen for vector subspaces. You could have just the 0 vector, you could have all of R2, or you could have a line through the origin. Vector subspaces of R3 are going to have 4 possibilities. You could have all of R3 or just the 0 vector, or you could have a line through the origin, or you could have a plane through the origin. So these are the 4 possibilities of vector subspaces of R3.